Welcome to this explainer. I am absolutely thrilled to have you here today because we're going to decode something that sounds, well, kind of like pure science fiction, but it's rapidly becoming our everyday reality. We're talking about how machines are learning to simultaneously see the world and read about it, and they're doing it at an incredible level. This is the absolute magic of vision language models, and by the end of this, you're going to know exactly how they tick.
So here's our roadmap. We'll start with teaching AI to multitask, dive into multimodal AI tasks, look at the architecture under the hood, explore training methods, check out superstars like DALL and Clip, and then peek into the future of vision language. Let's get right into it.
Section 1. Teaching AI to multitask. Let's introduce the real hero of our story today, which is the superpower of multitasking across completely different types of data.
At the very foundation of all of this is something called multimodal learning. Think about how you experience the world, right? You don't just read text or just look at pictures in total isolation. You combine them to build context. Well, multimodal learning allows an AI to do exactly that. It's the process of treating different statistical properties, like the pixels in an image and the actual characters in a sentence, as a single, unified input to the exact same model. Section 2. What can multimodal AI do? All right, let's move past the theory for a second and look at the specific jobs this AI hero can actually perform out in the real world.
There are basically three main domains here. First up, we've got generation tasks, where the AI is literally creating entirely new visual or text content from scratch. Next are classification tasks, which are all about interpreting and reasoning about the content it sees. And third, retrieval tasks. This is where the AI acts like a super smart search engine, finding specific visual information based on your text instructions, or vice versa. Let's take visual question answering, or VQA, as an example. If you ask an AI, hey, what color is the car in this photo? It isn't just matching text keywords. It actually has to physically process the image, identify the specific object as a car, determine its color, and then formulate an answer back to you in natural language. It's moving far beyond simple text prompts into true common-sense cognitive understanding. Pretty wild, right?
Section 3. Under the hood, architecture. Okay, time to peel back the layers and look at the actual brain making these crazy capabilities possible. To really understand the architecture, we've got to look back at a massive breakthrough in natural language processing called BERT. BERT was this transformer model, essentially a highly advanced pattern recognition engine that just completely revolutionized how AI understood text. And researchers brilliantly realized, wait a minute, we can apply this incredibly successful text transformer to vision tasks too. This sparked an absolute explosion of multimodal architectures. Suddenly, boom, we had models processing language and images at the exact same time. A good way to think about this is using a human brain analogy. Think of two-stream models, like VLBERT, as processing sight and sound separately in different parts of your brain before combining them. VLBERT uses separate modules for text and images, which then interact through this process called co-attention to figure out what's important. On the flip side, single-stream models, like VisualBERT, are like using one integrated neural feed right from the jump. It encodes both modalities within the exact same transformer module to instantly discover alignments between them. Section 4. How do we train them? Look, before an AI can start generating mind-blowing art or answering your complex questions, it has to go to school. So let's explore how we actually train these massive transformer architectures. To train these things, researchers use a whole combination of pre-training strategies. We have masked language modeling and next sequence prediction for text. We've got masked region modeling for images. But the real magic? That happens when we combine them. Methods like image-text matching and contrastive learning are essentially massive, high-speed matching games. We feed the AI millions of examples, reward it for pairing the right picture with the right sentence, and penalize it when it gets it wrong. Through sheer repetition and scale, it learns those underlying relationships between visual concepts and human language.
Okay, we've talked a lot about the theory and the computer science behind all this. But what does all of this complex architecture and training actually look like when you let it loose in the real world?
Section 5. Superstars. DALL and Clip. Let's see how all this math builds up into the famous AI celebrities that have been making headlines.
First up is DALL. Now, this model tackles visual generation by modeling the joint distribution of text and images.
It maps images to tokens using a complex encoder, which is a bit like creating a dictionary of visual patches. By combining these image and text tokens into a single data stream, DALL-E can read a completely novel text description and output a realistic image that has literally never existed before. No way, right? It's amazing.
And that logic powers the next evolution, glide and diffusion models. Instead of getting bogged down in heavy equations, just look at the logical steps here. Step 1. You sequentially inject random Gaussian noise into an image until it's just pure static. Step 2. You train the model to reverse that diffusion process, constructing beautiful, highly realistic novel images right out of that noise, guided by a text prompt. It's literally like unbaking a cake perfectly every single time.
Then we have CLIP, which is an absolute master of classification. CLIP is famous for doing zero-shot classification, meaning it can accurately classify images using labels it has never explicitly seen before in its life. How? Because it was trained on a staggering 400 million image text pairs using that contrastive learning matching game we mentioned earlier. It acts almost like a magnet, pulling together the correct image text pairs and pushing apart the incorrect ones, giving it this incredibly robust, generalized understanding.
Following CLIP, researchers decided to push the boundaries even further with Align. Align proves that sometimes bigger really is better. Instead of carefully curating the data, they scaled up, using a massive, noisy dataset of 1 billion image text pairs. They proved that the sheer scale of the dataset can actually compensate for the noise. This meant they could skip expensive, time-consuming data preprocessing entirely and still achieve phenomenal results.
Next, we have Florence, which is framed as an end-to-end foundation model. Florence is like a decathlete. It doesn't just do one thing well, it achieves state-of-the-art dominance across various benchmarks. It combines bidirectional learning with an advanced hierarchical vision transformer and a modified decoder. This makes Florence easily adapt to entirely different downstream tasks, going from object-level representations all the way to full video understanding. Now, while the text encoding side of these models is basically solved, researchers realize they need to actively upgrade the eyes of these models. That's where tools like VinVL and SimVLM come in. VinVL focuses on enhancing visual representations by detecting fine-grained attributes alongside objects, giving the model a much richer visual vocabulary. SimVLM, on the other hand, upgrades image encoding by using more advanced neural networks right from the start. Section 6, the future of vision language. We've seen the incredible capabilities and the crazy architecture underneath. So let's look at where all of this rapid development leaves us today and where we're heading next. Despite the absolute magic of generative models like DALL-E and the brilliant zero-shot reasoning of CLIP, the quote on screen really hits the nail on the head. The research community still has a long way to go. The immense big tech infrastructure and massive data sets required to run these models mean we are just at the very beginning of this journey. The foundation has definitely been laid, but it leaves you to wonder, if this is what machines can do today, what foundational breakthrough is going to happen tomorrow that completely reshapes how we interact with technology? Thanks so much for joining me on this explainer. Keep learning, and I'll see you next time.